Now let's have a quick recap of chapter 13. We considered two important terms. One is dissociation and the other is ionization. You need to remember that dissociation involves ionic substances. Example, sodium chloride would actually dissociate into sodium ions and Cl- ions. Okay, in dissociation there's no direct reaction between water and the ionic substance. Now with ionization, there is actually a direct reaction between water and the substance. Okay, so in ionization we can look at an example. Hydrochloric acid reacts with water forming H3O plus ions and Cl- ions. Okay, moving on to chapter 15, acid and base reactions. The first thing we look at is the Bronsted-Lowry theory, where we found that an acid is a proton donor and a base is a proton acceptor. Now let's look at some questions on this. Can we have an example of a strong acid that is also a weak acid? Yes, we can. Okay, if you look at sulfuric acid, for example, sulfuric acid is strong acid, and if it's diluted enough, it is still a strong acid, but it can also be dilute if it is diluted enough. So if a lot of water is added to, or a lot of sulfuric acid is added to water, it can have a lower pH. Okay, let's look at an example. Okay, let's move on to question 2. How do you find OH minus? We make use of Kw, which is the ionization constant. Kw is equal to OH minus times H3O plus, and which is 1 times 10 to the minus 14. Okay, and then we work with that. We have one unknown, which is the OH minus, and we try and solve it. So follow the working that follows. Okay, we get an answer of OH minus concentration equals to 10 to the minus 12 molar. Okay, now looking at question 3, remember that hydrochloric acid is a strong acid, will ionize completely into H plus and Cl minus. And to find the pH, we know pH is equal to minus log hydrogen ion concentration. Okay, looking at the equation again, remember that HCl forms 1 mole of HCl forms 1 mole of H plus and 1 mole of Cl minus. So 0.005 molar is going to form 0.005 molar of H plus and 0.05 molar of Cl minus. So that is why for H plus I use 0.005 molar. Now pH, and after working on the calculator, you get a pH of 2.30. Okay, now let's have a look at question number 4. We get to find the pH of calcium hydroxide solution. You're given the concentration. This is a bit more tricky because you've got 2 moles of OH minus. Okay, we'll have a look at the solution and then try and explain the solution. Calcium hydroxide will ionize into calcium 2 plus and 2 OH minus. Okay, remember it's 2 OH minus that forms. So this means that 3.3 times 10 to the minus 3 molar of calcium hydroxide, you're going to form 2 times 3.3 times 10 to the minus 3. That's based from the reaction stoichiometry. Okay, so from the OH minus concentration, we can use Kw and then find the H plus concentration. Once we have H plus, we can find pH because pH is minus log H plus, so you can follow the working. Okay, this now gives us a pH of 11.82. It does make sense because calcium hydroxide is a base and a high pH tells us that it is a base. Okay, now we'll consider another example, finding the pH of a solution of aluminum hydroxide. Remember, aluminum hydroxide is AlOH3, so there's 3 moles of OH minus. So this becomes a bit more trickier than the calcium hydroxide, but the procedure is the same. So now you can have a look at the solution. We get a pH of aluminum hydroxide to be 12. So I suggest you walk through this question and be able to understand it and work it out on your own. Okay, now have a read of question 6. You got an acid-base reaction. You need to determine all the conjugate acid-base pairs. Okay, we know that an acid is a proton donor and a base is a proton acceptor, and all acid-base conjugate pairs, they differ, or the only difference between an acid-base conjugate pair is a proton. Okay, so let's have a look at the solution. So HCO3 minus is an acid. Okay, it donates a proton, which is H plus, and it becomes CO3 2 minus. So that is one conjugate acid base pair. In this reaction, water is also a conjugate acid because water donates H plus and it becomes OH minus. So OH minus in this case is the conjugate base. Right. Have a look at the next question, question 6b. Amphiprotic, our understanding of amphiprotic means a substance that can act both as an acid and a base. So that means it can donate a proton and it can accept a proton. What we find here is HCO3 minus is an amphiprotic substance because in the first instance it can donate a proton minus H plus and become CO3 2 minus. And in the second case, in purple, the HCO3 minus can also act as a base and accept a proton H plus and forms H2CO3, which is carbonic acid.